Here Ax is congruent to B mod M. So first of all, we have to make a strategy to solve this, to find the number A bar such that here find the number A bar such that A bar A is congruent to 1 mod M, and this is called the inverse of A modulo M. If we know the inverse, then we can find the solution to the linear congruence by x is equal to A bar B mod M. For example, we are solving 3x congruent to 4 mod 7. So here you have to see that by the division algorithm, 5 into 3 equals 15 is equal to 2 into 7 plus 1 is congruent to 1 mod 7. This is the important point. And the inverse of 3 modulo 7 is 5. So multiplying both sides of the linear congruence by 5 gives x is congruent to 5 into 4 mod 7, congruent to 20 mod 7, congruent to 6 mod 7. So any x that is congruent to 6 mod 7 is solution, like in the example 6, 13, 20, minus 1, etc. If we check here, 3 into 6 is equal to 18 is equal to 2 into 7 plus 4 congruent to 4 mod 7. Same here, 3 into minus 1 is equal to minus 3, which is equal to minus 1 into 7 plus 4 congruent to 4 mod 7. So if we can find the inverse of A mod M, then we can solve the linear congruence. Ax is congruent to B mod M. The important questions are, does such an inverse always exist? And the second, if so, can we find it more systematically than our previous method of thinking really hard? If A and B are relatively prime, then an inverse of A modulo M exists. Here is the proof. Suppose A and M are relatively prime, so GCD of A and M is equal to 1. Buildup theorem tells us that there exist integers s and t such that sa plus tm equals 1. This implies that sa plus tm congruent to 1 mod m, but tm is congruent to 0 mod m, so it must be the case that sa is congruent to 1 mod m. So S must be the inverse of A mod M that we are after, and this proof also shows us how to actually find the inverse. The inverse of A exactly the coefficients from Buildup theorem, and we saw last time how we find such an S. Determine the inverse of 19 modulo 141. So by the division algorithm, a Euclidean algorithm, to confirm that GCD of 19 and 141 equals 1. So here 141 is equal to 7 into 19 plus 8. Same 19 is equal to 2 into 8 plus 3. 8 is equal to 2 into 3 plus 2. 3 is equal to 1 into 2 plus 1, and 2 is equal to 2 into 1 plus 0. Since the last remainder was 1, the Euclidean algorithm tells us that 19 and 141 are relatively prime, and theorem applies. There is an inverse of 19 modulo 141. Here 1 is equal to 3 minus 1 into 2, and 3 minus 1 brackets 8 minus 2 into 3. So 3 minus 1 into 8 plus 2 into 3 equals 3 into 3 minus 1 into 8. Same here, 3 into 19 minus 2 into 8 minus 1 into 8 equals 3 into 19 minus 6 into 8 minus 1 into 8 equals 3 into 19 minus 7 into 8 is equal to 3 into 19 minus 7 into 141 minus 7 into 19 equals 3 into 19 minus 7 into 141 plus 49 into 19 equals 52 into 19 minus 7 into 141. So here 52 is the inverse of 19 modulo 141.